Good morning, everybody. Good morning, YouTube. Right. So take home exam 3 was due today and is due today in principle, but all deadlines are elastic. And I'm certainly way behind in my own deadlines. I'm way behind in the grading. So, get it in when you can. I think they call this nowadays, they call this mastery-based grading, which means sort of, you're sort of graded on how far you get and get down as much as you can. Yeah, so here we go. I guess maybe that's almost a good thing, a good side effect of the pandemic, that we've gone to mastery-based grading. Okay, so PS11 is due on Monday because it is helpful to have deadlines of some sort, but of course they are elastic, so that's a good target. And oh yeah, so let me check on the chat here. So did everybody get my email about sort of having a lighter final and changing the grade percentages? Okay, and yeah, okay. So all right, so just let me know what. So I won't pressure anybody to answer now, but just let me know what you think, or if you have some alterations or suggestions. I think that's the way I'm going to go at the moment, but we'll see what. I want to wait and try to hear back from everybody. Let's see. So yeah. Oh yeah, and PS11 is due Monday, which means yes, that we're going to have a problem session on Friday at 10:30 at the usual time in the usual way. Okay, so any questions? Well, actually, so what? As promised, I am scheduled to scheduled to indulge myself. So let me, excuse me, first do our little one more time. Do our summary of Galois theory. So suppose, and it's all in black font because it's all done. So in a nutshell, suppose K is the splitting field of some irreducible little f and big F. So Galois theory relates the field theoretic properties of K as an extension of F to the group theoretic properties of G. The Galois group of K over F, remember, is a group of K of F automorphisms fixing every element of F of K. Yeah, automorphisms of K that fix every element of F. That's better. So one of those properties is that because F is irreducible, G permutes the roots. Because F is so G always permutes the roots of F, even if F is not irreducible, and is isomorphic to a transitive subgroup of Sn. The transitivity relates exactly to the irreducibility of F, is a consequence of the irreducibility of F. And the main theorem of Galois theory says that there's a bijective inclusion reversing correspondence. Look, I finally fixed this typo. Can you believe it? There, we must actually be done with Galois theory because I finally fixed the typo. So there's a bijective inclusion reversing correspondence between subgroups of G, which we've been writing over here, an intermediate field between K and F that sends H to its fixed field and sends a field L, an intermediate field L, to the Galois group of K over L. So the Galois group of the big field over the medium field, not the medium field over the little field. And again, if you want to look at what happens with the medium field over the little field, that's going to be Galois if and only if the sort of corresponding subgroup H is a normal subgroup. So Galois extensions down here correspond to normal subgroups. Well, I guess yes, also groups that are normal down here. In which case, the Galois group of the sort of extension over the bottom. Oh yeah, you can't even see my hand. Sorry. The Galois group extension over the bottom is equal to G mod H. Right. I hope these hand gestures are vaguely important. Well, they're at least make this faintly more visually interesting on YouTube, I guess. Anyway, so a typical problem, sort of a problem that you might sort of think about here, that you are thinking about a lot on problem set 11, for example, is that given a polynomial, compute its Galois group. This is, and when if you go get a PhD and you take your qualifying exams in algebra, this is going to be one of the problems. Something like that is one of the problems that you'll see. Like, here's a polynomial, go compute its Galois group. So the big question is that is when can those roots alpha 1 through alpha n be written as a function of the coefficients in f of f in expression using only kth roots, using only radicals. And if that happens, then we say that f is solvable by radicals. And the big answer to that is that, as we just saw last time, is that f is solvable by radicals if and only if its Galois group, the corresponding Galois group, is a solvable group. Ah! There we go. We did it! Yay! Okay, so now, so I have scheduled some other stuff here. You can see there's like, well, I'm sure you can see there's more slides coming. 2 of 16. So there's like a lot more slides coming that I could talk about and indulge myself. But instead, let me ask: are there any questions about Galois theory, about anything in Galois theory, about anything in chapter 16? Because I think if you have questions, it's probably more productive to answer those than it is for me to indulge myself as much as I find that amusing. So, questions? Okay, Ravi, go ahead. You have an off-topic question? You can ask it out loud if you want, or you just type it in the chat. Oh, this is like really off-topic. Is there an intersection between analysis and algebra? Oh, sure. Let's see. I mean, there's so many. Let's go through our faculty. If you just like think of what comes right off, Dr. Goldston, who's retiring, who basically that's his entire career. You can use analysis to solve problems in number theory. So if you took you took 131B. So 131B is sort of that's like the prelude to doing stuff like analytic number theory. That's what Dr. Goldston has done in his research. That's one. I don't know. I was actually just thinking about one such. Let's see. Well, let me answer this. Let me actually type out an answer to this. You know, this is like I was just buying this little piece of software here, the PDF annotator. This is like one of the best pieces of software purchases I've ever made. This is like saved my quarantine teaching. Okay, so intersections. Let me expand this a bit. Intersections between analysis and algebra. So one thing is that if you let's see, Fourier analysis, especially, it's like Fourier analysis plus number theory equals analytic number theory. And this is Goldston's research. So he's retiring, but that was certainly a notable person here who's done research like that. Dr. Shetler also, of course, does research in number theory, but his tends to be more on the algebraic side, as some of you may know. Let's see. Right. So see the Riemann hypothesis. So for some Riemann hypothesis, proof of Fermat's last theorem. That's the analysis is sort of in the background of this, but it's certainly related to the proof of Fermat's last theorem. Yeah, so there's that. Another thing that, let's see, something else that comes to mind. It's actually the same thing. Yeah, you can use, let's see. So you can use analysis. Well, I mean, yes, I guess maybe the answer is yes. And it's all the things I know about are all kind of the same area. You can also do Fourier analysis on groups. So you can sort of say So here's a possible, I was actually just like turning this over my head today, this morning for some reason, a possible thesis topic. And you hear the shape of a group, whatever that means. This is but I guess that, well, I don't make that too mysterious. It's really a Fourier analysis on finitely presented groups. Robbie, this is an excellent day to ask off-topic questions. Let's see. I mean, yeah, there are all kinds of other, let's see, analysis-based algebraic topology. So this, I only know a tiny bit about it. I know a little bit about this on some other aspect, but I only know a little tiny bit about it in the analysis side, but maybe just enough. This is the keyword here is something called L2 homology. Homology/cohomology. Yes. So there's all kinds of, so there's three things. Yeah, I mean, and each of these, so this is probably, if you're interested in this, I mean, this is not exactly Dr. Shetler's ballpark, but close enough, and he'd certainly be a good advisor for a thesis like that. This is something I've been thinking of. I have actually a very specific, here and here, I have very specific topics in mind for projects. Though I think though this would be me, as is like, and this would involve the learning some analysis, some more Fourier analysis, which I know, even though I wrote a book on it, I'm not really an expert in it. And for here, this is some how should we say, the project I have in mind for this is basically non-commutative ring theory. It's probably the most, not the most glamorous way to describe it, but the most accurate. Okay, so there's three intersections between sort of fancy analysis and fancy algebra, as taught over here. All of you are in sort of striking range of doing these. Oh, Robert, that's an excellent and flattering question. Will I write a book on graduate group theory? Well, that's actually going to be my indulgence for today. I'm thinking about it, so you'll see sort of where that's going if we go in that direction. Robbie, I'm just to get back to your question. I'm curious, why is there a particular reason why you're asking that question, or no reason? Yes, there. It's all it's all one, man. Yeah, it is kind of all one. I mean, there's sort of actually these two topics here. I mean, there aren't a lot of grand unified field theories in mathematics. It's just kind of hard to do those these days. But both of these two things here together are part of the closest thing to a unified field theory in mathematics, and that's something called the so this is something called the Langlands program, which is really, and it is, and you actually, and it's actually sort of, it's a big enough idea that you can actually see it in the newspaper, in like the New York Times described this way. It's a program for sort of unifying analysis and algebra. Man, it's all one. Yeah. Oh yeah, you're taking 230. Oh yeah, you guys are doing measure theory, and you're doing measure theory right now. Yeah. So that's all That's all the foundation of this. Like, it's all sort of lurking in the background. I mean, at least, to the extent that I have contact with these things, you have to have the measure theory in order to set everything up. But once you set it all up, you can kind of forget about it. Shh. Don't tell Dr. Hambrook I said that. But it's sort of true. I mean, unless you're Dr. Hambrook, in which case you do it for a living. Yeah, there is. Oh, well, you know what? Let me actually add it. Oh, that's right. I do know a connection there. So there's using class field theory. Remember we did that like 10 million years ago? We talked about the class group of imaginary quadratic number field. That seems so long ago. Class field theory to create examples in measure theory. This is actually Dr. Hambrook's most recent work, and so there we go. So yes, so there is. Are there? Oh, and Robert asked, are there possible master's theses in algebraic geometry? Yeah, but we don't have anybody who knows that. Probably the closest person we have is Dr. Shetler. I mean, you could just. I guess I'd be willing to do it just because I'd like to learn algebraic geometry, but it wouldn't be so exciting. It would just be like, well, let's you and I teach each other algebraic geometry, which would be fun. That's a different beast altogether. Okay, yes. So there's but I have to say, if you just name any two subjects in mathematics, are there intersections between them? Yeah, probably. There's just a lot of stuff going on out there. All right. Any other questions? Especially are there any questions about Galois theory? Okay, so let's just do something different, which we were just saying, as we were just alluding to. Here's geometric group theory. Okay, so I said I was going to try to indulge myself today, and so I wanted to give in our last two class sessions, especially because I want to sort of lighten up the load a little bit at the end. I'm just let up on the gas a little bit at the end here. I want to give like just a very brief sort of and perhaps shallow introduction to what's called geometric group theory. And just to be clear, you're not going to have any homework on this. It's not going to be on any exams. It just sort of sit back and you can just sort of sit back and enjoy it, or chill out, or I don't know, turn off your camera, put it on mute, and take a nap. It's okay. But just purely for fun, I want to introduce just some ideas of geometric group theory especially because I'll wake everybody up when we get to the intersection with Galois theory. But there is a sort of Galois theory idea that shows up later. Anyway, so geometric group theory is a study of groups that you get by treating them as geometric objects. And so here's a typical, let me introduce it algebraically. Because a typical group to study is called a free group. So have you guys seen the free group before? Has anybody seen the free group? Did that show up in 221A or 128B or anything like that? So that was 221A, you guys did the free group? Yeah, okay. Oh, good. All right, so you know this. All right, so so it wasn't 221, but if you sort of believe it exists, then this is not a big deal. Okay, so mostly let's introduce some terminology here. So let X be an alphabet, and a word in X is something like this. It's just so here's your alphabet, A1 through AN. Then you just have some way you just munch together some letters, possibly with inverses. And a reduced word is a word without an AI inverse or an AI inverse AI. So and why is so why is this called actually? So let me instead of using AI inverse, let me use ABC because it's a little shorter to write. So the reason why you talk about reduced words, A inverse. All right, so the reason you talk about reduced words is because in any group, if you have two elements C inverse, no matter what they are, they will cancel out, and so just the fact of being an element of a group means that certain relations hold, right? But a free group is one in which essentially no other relations hold. But okay, more formally, the free group is on n generators is given by reduced words in X, where X has an alphabet with that has n letters in it. The operation is concatenation with reduction. I'll explain what that is in a minute. The identity is the empty word written as which are as one, and the inverse is socks and shoes, which means something like, if you have A, B, C inverse. Y'all remember socks and shoes from way back in the day, from like your very first class in abstract algebra? Socks and shoes? Who remembers socks and shoes? Oh, okay. Right. So, well, when you guys teach algebra, as I bet some of you will, here's the thing to remember: is socks and shoes. So the thing about socks and shoes is, if you're gonna when you put on your socks and your shoes, you put on your socks first and then your shoes. But when you take them off, you take off your shoes first and then your socks. In other words, when you take the inverse of an element, I can get this to respond. Oh, there we go. When you take the inverse of an element, the inverse is if you take the inverse of a product, you get the product of the inverses, but written in reverse order because, well, yeah, because when you put on your socks and shoes, you take them off in the opposite order. So that's what I mean by inverses come from the socks and shoes idea. Let's see. So an example of, so just to give an example of, so why is it that the socks and shoes principle gives you inverses? Well, that's because say if you multiply ABC times C inverse B inverse A inverse by associativity, so multiplication is you just write the two words together and then you reduce them. So there, so this is, so in case, did you guys use this word in 221A, concatenation? Yeah, okay. Oh, there we go. So as you know, it's a fancy word for saying you just stick the words together. So yeah, so those can't. Right. So now those cancel out. Bing. And so we get A, B, B inverse A, and these cancel out. Bing. It's very important to make that bing noise. And so you get A inverse, and that's equal to 1. And so Robert, now you know what the free group is. You start off with a bunch of letters, and this is all you're allowed to do. And you know that you're done when all the words are reduced. Okay, so right, and right, and because I should say that you may be vaguely remember there was like more to it when you saw it before, but we're going to skip the important but boring part where we check this all works, right? Because we're just having fun, and it is important, but it is boring. But so yeah, eventually it all works. I mean, you might have to worry that, like, I guess I should say something about what you might worry about. So the worry you might have here, okay, the worry that you should have if you're being careful, worry. What if you reduce differently? So yeah, so the worry that you should have when you see this sort of this quote definition unquote, is that you might look at this and say like, well, okay, so I reduced this in some way and I got the identity. Maybe I could reduce this in some other way and get something else magically, or like get stuck at some other point. But it works. It's fine. Yeah, I mean, really, I mean, morally speaking, you should be worried that this will all somehow work out to be inconsistent, but it's okay. It does turn out to be okay. And the semesters, I was going to say, life is too short. And life is not too short to do the occasional boring verification, but the semester is now too short to do one. So is everybody good with the free group? Okay, so and now it occurs to me that you may have done this already. So let me here I wanted so sort of the goal for today, or like however long this takes. Maybe this might sort of leak into Monday a bit, is to prove the Kurosh subgroup Kurosh, I think it's Kurosh subgroup theorem, which says that every subgroup of a free group is free. And so for simplicity, I mean, there's a little bit of a fudge here. I mean, we're really going to sort of focus our attention on the case of a subgroup of finite index, but everything works in general. I mean, but there's just a sort of a little infinity stuff that we have to that has to be done more carefully. So did you guys do the Kurosh subgroup theorem before in 221A? I guess I would actually be almost surprised if you didn't, because what else is there to do with free groups? So Apurva, so you said this seems vaguely familiar. Were there pictures involved? So there probably, do you remember if you saw pictures with this? Because if you have seen the Kurosh subgroup theorem before, yeah, right. The fundamental group principle. Oh, did you do in topology? Oh my goodness. Oh well, right. Right. So we're actually going to do that today. Oh well, you'll have seen some of this then. Well, Apurva, you'll have to wait until Monday to see something. So who's seen this stuff in topology? Because that is more or less what I'm going to do today. Yes. So oh yes, maybe you have seen this with cartoons. Well, because that. So I guess. So the goal for today is I want to prove the Kurosh subgroup theorem by drawing cartoons. And so, Robert, you're asking like, am I sometime going to write a book about graduate algebra? My book project. So the book project I have in the back of my mind is Geometric Group Theory, the graphic novel, more or less. You might have to add more text than a comic book. Usually would, but it's the graphic novel, the comic book. That's a better title, actually. Anyway, so let me just ask you. Let me actually pause and ask everybody. So who has seen Kurosh and who has seen it with pictures? I've actually never seen a non-pictured proof of this. I have no idea how you would prove this without pictures. We're actually going to try to make it look easy with pictures, I hope. We'll see how far. See if this breaks down in the middle. I only like semi-prepared this, so we'll see what happens. So go ahead and answer in the chat who's seen this before and who's seen it with pictures. So Apurva. So no. Okay. So all right. So yeah. So Apurva, where did you see it? Do you remember? Or see something like this?
I'm not really sure actually. I kind of thought of like I think it might have been at a camp or something,
Oh,
but
at a camp. Yeah, that makes sense.
yeah.
Okay. So this is going to be pretty similar, right? Maybe. Um, yeah. Stop me. Well, okay. So don't stop me when you've heard this one before. But yeah. So right. You mentioned this is so you mentioned that this has something to do with like the fundamental group of topology, and so what I'm going to the sort of real. I mean, there's one part of this where I'm really going to start so there's one part where we sort of swept everything under the rug, which is like we have to verify the free group really is a group. Okay, it is. And you saw the last semester, that's okay. But the other part we're going to really sweep things under the rug is that I essentially have to what I'm going to try to do is I'm going to sort of reconstruct the beginning of algebraic topology in the fundamental group without using any topology. So here we go. Okay, so yeah, now with cartoons. All right, so I want to talk about so I have to do some work at some point. So here it is. So let X be a label, an alphabet. So we're going to assume that all. So I'm just because I'm going to forget to say this a bunch of times. In this today and on Monday, we're going to assume that all graphs that we discuss are connected and directed. So directed. Just to make sure we're all on the same page here. Directed means that all edges have little arrows on them, and connected means you can always get from one place to another. And X is often we're going to often think of it as being like A, B, C, yada yada. Okay, so an X label graph is a directed graph gamma whose edges are labeled with elements of X such that no two edges. Okay, so no two edges coming into a vertex are labeled with the same letter. All right. Oh goodness. So all right. So if you have two edges coming into the same vertex, then you can't label. Oops, I forgot to do the forbidden thing. So if you have two edges coming into the same vertex, you can't label both of them with A. So that's rule number one. You can't. There's at most one edge coming into a vertex that's labeled with A in a very similar way. There's at most one edge coming out of a vertex that's labeled with A. So that's also forbidden. And but what is okay, and actually is sort of necessary, as you'll see later on, is sort of typical, if not always necessary, is that you kind of expect there at a vertex, you kind of expect there to be one edge labeled A coming in and one edge labeled A coming out, and so this case is okay. So so does that labeling rule make sense? Like I said, cartoons. There we go. Okay, so that's what it means to label a graph with an alphabet X. So now, if we look at a base-pointed label graph, is just a label graph, and you pick one particular vertex of gamma, and which we call the base point. And that's necessary. Well, we'll see why that's necessary in a minute. Base points are actually base points make life very difficult sometimes. And I guess the sort of short way, if let me put in a mantra here, that sort of base points equal conjugation. And I think we might even sort of do that, use that on Monday. But base points make life difficult. And that's sort of, it's very closely, I mean, as you can see, since base points, as we'll see, relate to conjugation. We already see that. Oh yeah, that's right. We have already seen this actually. So if you look, there's essentially this topic shows up in C permutation groups and the normal permutation groups in the normal part of the main theorem of Galois theory. So if you look, if you sort of look at what's going on in the normal part of the main theorem of Galois theory, if you look at that proof, what's actually kind of going on there, the reason that it's the normal, remember, it's the normal subgroups that correspond to the Galois extensions of the base field, and sort of the reason that happens is essentially because if you're sort of looking to stabilize, when you look at the stabilizer of a different root of the same equation, that same polynomial f, then you get a conjugate. And so yeah, that I know I'm getting getting a little cosmic there, but yeah. So just maybe keep in the back of your mind that yes, base points equal conjugation. That's your Zen koan for the day, or probably one of several. All right. So let's just maybe more literally. Are there any questions about the definition of an X labeled graph, an alphabet labeled graph so far? Okay, so yeah, there's just so far there's just this one rule. Oh yeah, so that, like I was saying, completely a completely X label. Oh, so there. So without the third picture, all edges are distinct. Yeah, I mean, you definitely have to distinguish between the in edges and the out edges. Yeah. So right, and so yes, you have to be very careful about distinguishing between in out edges and out edges, because it's sort of, as we'll see, it's essentially the difference between multiplying by a. Well, it's not essentially; it's the difference between multiplying by a and the difference in multiplying by a inverse. That's how the way we sort of indicate that in these graphs I'm about to draw is by the direction of the arrow. Does that make, Robert? Does that make sense? Okay, so yeah, that's where we're going with this. All right, so now let's talk about a completely X-labeled graph. I kind of alluded to this just a minute ago. So for every vertex and for every element of your alphabet, there's exactly one edge coming in and exactly one edge coming out. So I want to just sort of make up an example. So let X, so I'll have A, and let's see if I was wondering if I can pull this off. Oh my goodness, maybe I can do this. So if I'm going to try drawing with two hands and see if I can do this at some reasonable speed. Okay, so I want to draw an example. What I want to do is I want to draw an example of an X label graph, and I'm just going to make one up here. Call it 1, 2, 3, 4, 5. Okay, so now, so here's how to make an X label graph. So what happens? And you're going to help me do this. Oh yeah, let's make our base point 1. I guess that makes sense to make the base point 1. There's a star, so that's our base point. So I'm going to make a base pointed, completely labeled graph. And all right, so here's our sort of legend for the map, so to speak. A, so a red directed edges are A. I just don't want to keep writing A and B if I don't have to. So red directed edges are A, and blue directed edges are B. So does that make sense? A is red, B is blue. Okay, so now, so somebody type in a number between 1 and 5. 4. Okay, so A has to go somewhere from 1. So let's send it to 4. Different number, somebody else, or Trent, you could keep going. 5. Okay. Next. Just keep typing two. Well, yeah. So next. So right. So let me say where you cannot go. So you can't go. Well, let me make a mistake. Oh, this will be good. Actually, it's important to make a mistake. So you could say, well, what if you go back to 4? Right. But if I go back to 4, then we have 2 edges coming with the same label coming into 4. So that's no good. So it has to be one of the remaining. Well, you can't go. You just can't go. Right. You can't go into some place that already has a red edge going into it. So what's left? Somebody type in something. 1. Okay. And now we've closed up. And so so that's one thing. Okay. So somebody else tell me where should 2 go? 3. Okay. And then, but then there's no choice. 3 has to go back to 2. All right. So so that now yeah. So it says that for every vertex and every label, there's exactly 1 edge coming into V labeled A, and exactly 1 edge coming out of V labeled A. And so we got that done. And so now let's do B. Actually, let me darken the vertices a little bit here. There we go. All right. So B. Somebody type in a number from 1 to 5. So why can 2 go back to 3, but 5 can't go back to 4? Well, yeah, 3 went back to 2 because so the collision. Let me sort of in green. Let me put the problem. So 5 can't go back to 4 because this collides with this contradicts the fact that 1 is already going into 4. Right. So 5 can't. Yes, you can allow loops. So so one thing. Yes, in fact you definitely have to allow loops. So let's do that actually. So let 1. So self loops are okay. That's so that, let's see. So where should 2 go? Oh, but sorry, yeah. So Robbie, did I answer your question? So so this is impossible. So you can't do that for A. Oops. So you can't what the thing the green edge I wrote is you can't. Oops. You can't. I can't draw on the screen because the text box chat box is interfering. You can't do this for A because it contradicts the fact that there's already a red edge going into 4. So Robbie, does that make sense? Yeah, excellent question. Okay, let's finish up the blue. Yes. So so yeah. So where should 2 go? Two 2 goes to 3, and now okay. So so because I want everything. We do want everything to be connected. So 3 can't go back to 2 because then 2 and 3 are their own little orbit, their own little island. So where should leaving out 2? Where should 3 go? Somebody else, or Trent again. 4, okay. And where should 4 go? Well, I think you get the idea. So can 4 go to 2 and 5 as a loop? That's good. That's great. So that is in in the terminology that we're using here, this is now a completely, oh, actually, I should just type this. This is a completely AB labeled. Excuse me. Okay, so does that make sense? Okay, cartoons. Yay, it's cartoon day. All right. So yeah, how many times will I yell cartoons in this? All right, so paths in an X labeled graph. A path a path in gamma is specified by giving a starting at vertex and a word in X. Though not in general, not every such description corresponds to a path. Let me say, oh yeah, I should. If X is not completely labeled, or if gamma is not completely labeled, if gamma is not completely labeled, then it's the case. Then what can happen is that let me actually just copy some of what's going on here. I'll do some of it. Let's see. So and I'll just leave out the numbers. So what we have here is we have this and this. So leaving out the numbers, here's our base point, and there were two other vertices out here, and let's see, and there was, oh, whoops, oh no, that's fine. So what happened here was roughly that we had this, ding, ding, ding. So that's what we ended up here, and we ended up with a 2 cycle over here. And so that was A, and then B. So let's see, B was, oh yeah, there were self loops over here, and and let me actually, yeah, like that. Okay, so that's most of the previous example. So and so one so let me just quickly point out sort of what can go wrong here. I think we called we call this 2. So here, let me just go right to the point where because if you start at 2, you can't the B doesn't give a path because there's nothing coming out of, there's no B edge coming out of 2, but in general. So let me just draw something. So let's start at 1, the base point, and somebody give me. So I just need a string of A's and B's and A inverses and B inverses. So just go ahead, start typing something. Somebody type in A or B, or A inverse or B inverse. A. Somebody else? A. B inverse. And let me do A inverse. And I think that'll illustrate enough what's going on. Okay, so A, B inverse, A inverse. And so what path is that? Well, that So that gives us, so step one, oops, that's not what I wanted to do. I want to do this, okay. So, so A, this is, I'll use a little double arrow to indicate the path that we're going. So step one goes A, oh, except I did that wrong. Whoops, I did that wrong. Well, mistakes are illuminated because instead of going in the A direction, I went in the A inverse direction. So let me fix that, okay? Oh my goodness, and I erased that. That's fine though. So that was starting at 1. That was A, B, inverse, A inverse. So that's A, B inverse, A inverse. And now let me try that again. So as I was saying before, I so rudely interrupted myself. So if I start at 1, and remember this is 1 over here. Oops, no. This is 1. The base point is 1 over here. Then if we draw that path, then we go A. That was step 1. A. Step 2. B inverse, and B inverse means we go in the other direction of the arrow. So that's step 3. And A inverse. Well, either A or A inverse goes up there. So A inverse step 4. I'll be like unusually careful here, but it just needs a little harder to draw. So that it really goes along with this line here. So this is step 4. Okay, so does that? Yeah. So that gives the indicated green path. So that makes sense. Words give you words give you paths sometimes, because if we then try to do B from there, then B can't go anywhere here. Okay, all right. So we have label graphs, completely labeled graphs, and paths. All right. So definition: a loop in gamma is a path that starts and ends at the same vertex. Right, so this is not a loop, but I guess how could we get home from there? So let me actually try to. Oops. So how do we get home from there? If we started, if we had a loop at 1. You could do that same A, B inverse, A inverse. And how can we get home? We can get home by going through B inverse A. B inverse A. So that's an example of a loop at 1, which I won't draw because there'll be like too much going on in the picture. So, but does that make sense that gives you a loop starting at 1? Yeah, now you can see the whole thing. So and then B inverse A, and then we get a loop. Okay, so now let's talk about the fundamental group. I can now define the fundamental group. Sort of. I mean, okay, so if you take topology, if and when you take topology, everybody should take topology because it's awesome, especially since Dr. Campisi teaches it here and she's awesome. You'll find some sort of more formal definition of this that isn't dependent on cartoons. But you know, in the end, this is what you do. Well, at least, okay, this is what I do. Dr. Campisi actually works with topology. I'm not really capable of much more topology. I think I had one I've written one paper where I actually had to do point set topology, and it was so painful. And my co-author and I just like slaved for like weeks and weeks and weeks over this like one paragraph. And I'm not sure we ever quite got it right, but okay, it was close anyway. Yeah, my point set is not so great. I should teach it. I've learned a little better, or teach it again. I sort of taught it before. But the cartoons I know, like the cartoons I'm good at. So let's talk about it. So let F be an X label, an alphabet label graph with base point v sub 0. So the fundamental group of gamma written pi 1 of gamma sub v sub 0. And as you'll see, this fundamental group really depends on that base point. That's important. Is the following. The elements of the fundamental group are reduced loops starting at v sub 0. Well, this looks familiar, doesn't it? The elements are reduced, instead of reduced words, they're reduced loops. Okay. The operation is concatenation, where you do, well, I should draw a picture of that, huh? So concatenation is that you travel through some path G, and then you do another path H. Or actually, wait, that's misleading because these are actually loops, right? So I should go fix that. So here's your base point. If you do some loop G, and then you do another loop H, well, a loop is just, a loop doesn't necessarily have to look like a single circle. It just has to, a loop is just a path that begins and ends in the same place. So that gives you a loop. I just go, instead of going through in some sort of straightforward way, I go through zoop, and I go back home, and then I go zoop. As long as you start at home and end at home, that's a loop. The identity is the empty, this shouldn't be the empty word, it should be the empty path. Path 1, in which you don't go anywhere. Well, I guess it's the empty. Actually, empty word is okay, which means the empty path. Yes, the path where you don't go anywhere. A path we all know too well in these days of quarantine. Yes. I guess it's the empty loop. Well, because as we all know too well, if you don't go anywhere, then you start at home and you end at home. All right, so the empty word represents the empty loop, and the inverse of loop is the same loop except you go backwards. And so yes, so as you might, that should seem familiar from about, I don't know, half an hour ago, and so let me make my alphabet ABC like so. So that's there's my legend ABC. And so F3, the free group on 3 objects is the following, oops, I didn't have orange there, is the fundamental group of the following, oops, and I think I left something out of the definition. So let me go back, I'll go back and fix that in a minute. So yes, so Mengru, you're asking, can you have self-loops? It's very important that you have self-loops because the most important example, probably the most important example of a graph whose fundamental group you want to understand is this is what you might call the n-leaved rows. This is the 3-leaved rows. Yeah, so the free group, oh yeah, F3, if you don't remember what that was from about half an hour ago, it's the free group of rank 3, free group on 3 objects. Is the fundamental group of pi 1 of the 3-leaved rows. Well, there's only one base point, but I guess star. There, star. Okay, but I left out a word here. So I left out a detail here. So it's the operation actually concatenation. Yeah. No, I don't. That's too small to put it there. Okay, so let me. So concatenation with reduction. Just as the operation of the free group is concatenation with reduction. So yeah, so elements are reduced loops, which correspond to reduced words. And the operation is concatenation with reduction. That's not a good place to put the arrow. There. Yeah. So, and I guess I should say, in case you're wondering, I think probably you know what you see what a reduced loop is, but just in case it's not clear, reduced path actually is there's no backtracking. No, like no A inverse. Oops. Right. So so that yeah. So here this is a so we could so when over here we could have gone A B inverse B. You could have just done sort of the reverse, like exactly the reverse of what you just did. But what would be the point? You could have just you haven't done anything new. You just sort of went up on an edge and come back. And so if there's no backtracking, then yeah. So so we might as well, if you have a given path in a particular loop, you might as well have a loop with no backtracking. And so the elements are really reduced loops. Okay. So and I hope you can see that just almost by definition, this is the same. This is going to be the free group of rank 3, just because, well, that it just sort of maps one-to-one onto the stuff that you use to define the free group. Okay, so there. So that's a fundamental idea. How far off are we from? We won't quite finish today, but that's okay. We'll get pretty far. So this is a good point to pause and take stock. So does this make sense, the idea of the fundamental group of a base-pointed X-labeled graph? And are there any questions either about the definition or about this particular example, that the free group of rank 3 is the fundamental group of the graph with one vertex and 3 leaves coming off of it? Is everybody good to move on? Oh. Okay. So Robbie, you're saying this graph represents a group. So it's not that sort of the graph represents the group, in that it represents the group in that. Oh yeah. So did you guys do in 221A? Did you guys do generators in relations with pictures? Ravi, is that what you're sort of asking about? Yeah. So what happens is, if you do, suppose you do that in the sort of simplest possible case. Let's do it without the picture, without the stuff, filling the stuff in, right? So there, the relation. Remember, so the generators corresponded to like graph elements, and the relations corresponded to two cells. Well, if you leave out the two cells, you get what you get is you get the theory of generators and relations without any relations. That's the free group. And you'd think that you wouldn't be able to get anything out of that, right? That seems weird. But as we'll see, you can actually get, believe it or not, you can make significant progress without even using the two-dimensional stuff, just with the one-dimensional stuff. I mean, and you can put in the two-dimensional stuff, and it sort of becomes it's harder to draw, and so you can't sort of draw a sort of a detailed global picture, but it still works. Anyway, good question. Yes. So yes, if you remember this from 221A, yes, you have seen this before. This is the thing about generators and relations, except there are no relations, and so that's just it. Any other questions? Okay, so now let's zoom in again. And let's see how this goes. Okay, oh yeah, so now we're gonna talk about trees. So trees. Yeah, and I think, let's see how careful I am. I'm actually gonna end up being. So just so everybody knows what a tree looks like. So the idea is that a tree, well, look, this is both a tree and it's kind of telling you why it's called a tree. It looks vaguely tree-like, but there's the root. There we go. So let gamma be a labeled, connected, and directed graph, as they all are. So they are. I guess I should say this is an X-labeled, connected, directed graph, and the following are equivalents. One, gamma has no reduced loops. Let me point out that any. So here's what. So in green here is I'm going to draw a non-reduced loop. So because you can always find a loop in any graph, you can just sort of wander around, go up here, right? So there in green is a non-reduced loop. But you can, as you can see, why is it non-reduced? I hope you can see over here. So, for example, up here on this leaf, you have there's a backtrack. And let's see if I prepared this well enough, or am I going to totally flail on this? Totally possible. Working on the net here. It's okay. We're all just having fun. This is recreational now. Okay. Anyway, so the following equivalent: one, gamma has no reduced loops, and for n. Oh, right. And okay, there's an error here. And so the second is there exists a unique reduced path that starts at V and ends at W. Okay, so right. So right. So let's do a literal sketch of this proof. So let's say 1 implies 2. So the idea is that assume gamma has no reduced loops. Assume gamma has no reduced loops. So suppose we have two reduced paths that start at V and end at W. So let me draw that. Here's V, and here's W. And suppose there are two ways. Yeah, let's not even assume that whether they're equal or not. Let's suppose there's two ways to get from V to W. So there's the path, I don't know, P1, and there's the path P2. There's P2. So now we observe that P1, P2 inverse is a loop. It's a loop. It's a loop in starting at V, and so there must be a backtrack in it somewhere. Oh, I could. Oh, yeah, right. So none. So this is no non. So this is as some of you may know, I like to write. I like to write books, and now you're seeing what the first draft of the book always looks like. Maybe this is like the 0th draft. Non-trivial reduced loops. I suppose the empty loop is a reduced loop because there's no backtracks in it, but there's no non-trivial reduced loops. So P1, P2 inverse is a loop, so there must be a backtrack, but P1 and P2 are reduced paths, right? So the backtrack, it must be at the end. Oops. So there must be a backtrack in that loop. And it has to be at the end. And so, so let me sort of blow up the end here. So I'm going to take a magnifying glass and look at what happens at the end. So if we look very carefully what happens at the end here, which I fortunately actually kind of glossed over, it must be that both P2 and P1 are coming into W along the same line. Yeah, so there's W. And so there's a backtrack. So just in a very sketchy way, maybe both sketchy both in the sense of no, it's not so sketchy morally, but it's just totally an outline. So we can shorten P1 and P2, and the theorem follows by, or this half of the theorem, the proof, this part of the proof follows by induction. Right. Yeah. So so it follows by induction that okay. Well, I mean, I guess we could have assumed that P1 that the shorter of P1 and P2 is a minimal counterexample, is a shortest possible path that has a sort of non-trivial that has a distinct partner. And so, but we just made it shorter, and so it must be that. Yeah, there we go. And then we get a contradiction. Anyway, so that means 1 implies 2, and 2 implies 1 is exactly the same way. If you had a non-trivial reduced loop, oh yeah, actually 2 I guess 2 implies 1 a fortiori. Oh, I guess we're done. Gee, that worked out okay. I read this a long time ago, this proof. I guess I remember it a little bit. So 2 implies 1 a fortiori. Well, because of the case of the empty path. Right, the empty path is a reduced loop, is a reduced loop, and so you know, if you know that there's only one reduced path that starts at V and ends at W, then you can't have a non-trivial reduced loop. It's sort of a fortiori. So look, I guess that's actually a proof. All right, and so yeah, and so we've now we have defined what a tree is, and I guess that's not a terrible place to end. Look at all these cartoons! Wow. So let me just since I have -1 minute left, let me just sketch you what's going on here. So if you so the retract lemma is going to say that if you have part of your graph that's a tree, and there's some maybe extra stuff on it, 2, 3, 4. Then what this tells you is that if I take that tree and I shrink it down to a point, And you can see, so this is 1, 2, 3, 4 other edges sitting out there. If I take it, shrink it down to a point, then I get that, yeah, then I get something with an isomorphic fundamental group. And so that's, I guess, and I think I just really want to say that, that pi 1, their fundamental groups are the same. So that's where we will start on Monday in our last class. We're talking about the retract lemma and its proof. And yeah, so sorry, I went 2 minutes over. Thanks for your patience, everybody. So I will, I'll stop share and stop recording. And bye. Bye.